the clock. Three now. Hello, Upperwood. Okay, can you hear me on Zoom?
Yeah.
Okay, great. All right, I share my screen. A couple more people joining. Okay, so I'm sharing my screen now.
I never saw you, but I left here like right before 12:30, so that's why.
All right.
I did it last year, so.
Okay, go ahead and mute your microphone. Okay, so today is National Dog Day. I don't know how many of you do that, but what is a chemist's favorite dog breed?
No.
It's a lamb. A lamb.
Oh no. When is it? Oh, has she said yet?
It's a lamb. It's a lamb. Speaking of lamb, we're going to have a lab tomorrow. It's recrystallization from the General Organic Lab Manual. And the only compound to look up is that one that I listed last week called acetamide. Okay, make sure that you wear proper lab attire, no shorts, no sandals. Okay, it may be easy to forget with it being so warm outside, but you wear regular shoes and no shorts. Okay. Got a couple more people joining. There we go. Okay. Right. Hello, everyone.
Oh, honey, Tristan, sweetie.
Okay, so again with right, so today we're going to review quickly some of the things we talked about in terms of acids and bases, intermolecular forces, and then we'll introduce the idea of functional groups. Okay, those of you on Zoom, can you see the screen?
Yeah.
Okay, great. Okay, the three main types of intermolecular forces that we'll be looking at in this course, besides ion-ion and ion-dipole, include dipole-dipole, London dispersion, and hydrogen bonding. Right, dipole-dipole interactions will occur if we have a polar molecule, such as chloromethane, okay, where the electron dense end of one molecule is attracted to the electron poor end of another molecule, like a little bar magnet. Okay, so in chloromethane, there's a high electron density around the chlorine, and then there's a low electron density partial positive charge on the other side. London dispersion is also a type of dipole-dipole force, but it is transient. Okay, it's a temporary dipole. Okay, there's a random distribution in a nonpolar molecule. There's a random distribution of high and low electron density. And as molecules approach, they can induce a temporary dipole in a nearby molecule. Okay, with these three compounds, these are called isomers. They have the same molecular formula, but they have a different structure. There is a definite effect of branching on the boiling points. Okay, these all interact with other molecules of the same compound by London dispersion. Okay, they don't have any polar groups. They have zero dipole moment. But with normal pentane, you have much more surface area that can come in contact than with, say, neopentane. And the result is that for neopentane, the intermolecular forces are stronger, and so therefore it takes more heat in order to transfer this into the gas phase. So normal pentane has a boiling point of 36 degrees, whereas neopentane boils at 10 degrees Celsius. Okay, so branching lowers the boiling point, okay? All other things being equal. Hydrogen bonding is an especially strong type of dipole-dipole interaction. You have to have an NH or an OH to be able to form a hydrogen bond. Okay, so here we have methanol, which can hydrogen bond. There is a high electron density in this lone pair, and that's strongly attracted to a hydrogen on a nearby molecule. Okay, this is an especially strong type of attraction because you only have 2 electrons in the valence shell, and then you have a single proton in the nucleus. Okay, dimethyl ether, which is the compound on the right, contains oxygen, but it does not exhibit hydrogen bonding. Okay, there is no OH bond. Okay, and you can see that's reflected in the difference in boiling points compared to ethanol. Okay, once again, with ethanol and ethylamine, both of these exhibit hydrogen bonding. But oxygen is more electronegative, and hydrogen bonds are stronger. So you see a higher boiling point in ethanol than you do in ethylamine. Okay, I'll just briefly mention, we went over this last time. Like dissolves like, polar solutes dissolve in polar solvents, nonpolar solutes dissolve in nonpolar solvents. Okay, for a polar solute, a nonpolar solvent, the attraction between, in this case, ions is much stronger than anything we would get between an ion and a nonpolar molecule. Okay, typically the explanation that's given for nonpolar dissolving nonpolar is that you have random mixing, you have an increase in entropy when these dissolve in each other. Okay, and here water does not dissolve in some nonpolar organic solvent. Okay, because that would require breaking up the strong hydrogen bonds. I'm going to skip over Arrhenius. Bronsted acid is a proton donor. Bronsted base is a proton or H+ acceptor. When a Bronsted acid-base reaction occurs, you obtain the conjugate base and the conjugate acid. Okay, there's a change not only in the number of hydrogens, but also in the charge. Okay, so sulfuric acid loses an H and a plus, so it becomes HSO4 minus. Water gains an H and a plus, so it's hydronium H3O plus. Okay, an acid strength is expressed as the extent of ionization in water. Okay, so a strong acid is one that's almost entirely ionized. Some weak acid, HA, is only partially ionized. The extent of ionization, the strength of the acid, can be correlated to the Ka, which is an equilibrium constant. And it is equal to hydronium times the conjugate base over the undissociated acid. We leave water out of the equation. Okay, so the larger the Ka, the stronger the acid. pKa is minus the log of the Ka. And so HCl, for HCl, Ka is 1 times 10 to the 7th. pKa is minus 7. Okay, so the smaller the pKa, the stronger the acid. So these go in opposite directions. And then down here we have methane, CH4. Its pKa is 50, which means the Ka is 10 to the minus 50th. Okay, so that's an extremely weak acid. The stronger the acid, the weaker its conjugate base, and vice versa. Acid-base reactions will favor the weaker acid and the weaker base. Okay, the weaker acid and weaker base will always be on the same side of the equation. But that's the way the equilibrium is going to shift or favor. Okay, the weaker acid has the larger pKa, and the weaker base would have the larger pKb. Okay, you can actually compare either one, either the acids or the bases, to determine which side of the equilibrium is favored. Okay, so in this example, we have acetic acid reacting with sodium hydroxide. We can compare the acid pKa's. The acetic acid is 4.74. Water is 15.7. A larger pKa, so water is clearly the weaker acid. So that's going to favor the products. Okay, in this example, if we Okay, we could compare either the pKa or the pKb. In this case, water is acting as the acid, 15.7, and then on the product side, acetic acid. Acetic acid has a smaller pKa, it's a stronger, and so the equilibrium in this case is going to favor the reverse. The reactants are favored. Okay, I don't believe we talked about this last time, so this is new. Solvent effects on acidity and basicity. Okay, water is an example of an amphoteric substance, which means it can act either as an acid or a base. If it gives up a proton, it becomes hydroxide. If it gains a proton, it becomes hydronium. Okay. So the solvent that you're carrying out an acid-base reaction in will limit either what acid or what base can exist. Okay, so if the solvent is water, the pKa of hydronium is negative 1.7, and hydronium is the strongest acid that can exist in water. Okay, which means that, let me go back a few slides here to our table. Here we go. Okay, so water is 15.7. So hydrochloric acid, being a stronger acid than water, hydrochloric acid cannot exist. So it dissociates all the way to hydronium. All right, the strongest base that can exist is the conjugate base of the solvent. Okay, so anything stronger than hydroxide would immediately grab a proton from water and become hydroxide. Okay, so here is hydroxide. It's a little more than halfway down the chart. Okay, so anything down here, ethoxide, amide, methyl anion, these cannot exist in water. Okay, so if you put those salts in water, they're immediately going to grab a hydrogen from water and become hydroxide. So hydroxide is the strongest base that can exist in water. Okay, and in general, the strongest acid that can exist in any given solvent is the conjugate acid of that solvent. So for alcohols, it's ROH2 plus. Okay, alcohols will vary in their pKa's or pKb's. So this is kind of an average value, negative 1.9. Ethers can accept a proton to become this oxonium ion. And the strongest base that could exist in liquid ammonia would be NH2 minus. So if you have anything more basic than NH2 minus, it's automatically going to take a proton from ammonia and become NH2 minus. So this is the limiting or leveling effect of the solvent. Okay, so these are some trends to look for in comparing or predicting strengths of acids. Okay, one factor is electronegativity. Okay, so as electronegativity increases as we go across a row, acidity increases. So HF is a stronger acid than water, which is stronger acid than ammonia, which is stronger acid than methane. The weaker the acid, the stronger its conjugate base. So CH3 minus is the strongest base. F minus is the weakest base in this series. Okay, so a more electronegative element bears a negative charge more easily, which in turn gives a more stable conjugate base. And the conjugate acid would therefore be stronger. Okay, for a binary acid, the size of the anion can affect acidity. Okay, we just said that electronegativity was a factor, but in going down a column, electronegativity actually goes down. Chlorine is less electronegative than fluorine, bromine is less, and iodine is less. Okay, so something else is going on here. Okay, once the proton leaves, you've got an anion, and because of the large size of the iodide, okay, it can spread out. It can distribute that charge much better than, say, a fluoride ion, in which it's more tightly held to the nucleus. Okay, so being able to spread out the charge. Also, we can explain this in terms of orbital overlap. A fluorine atom is actually about the size of a hydrogen atom, so they actually have similar sizes. The reason for that is that as you add protons across the row, that pulls electrons in closer to the nucleus. Okay, so this is a strong bond. With HI, you have a very diffuse electron cloud, a very diffuse orbital, and so the overlap with the hydrogen 1s electron is not very strong. Okay, so this shows some different pKa values. Note here that HF is actually a weak acid. Okay, pKa is 3.2. These are all strong acids. They have large negative pKa's. Okay, so as we go across the row from left to right, acidity goes up. Okay, as we see a similar trend in the third row and the fourth row. As we go down a column, acidity goes up. So H2S is more acidic than H2O and H2SE, and then we have H2TE, for example. Okay, so going down a column will increase the acidity for a similar series. Okay, next we'll look at what we call inductive effects. Okay, these are effects of nearby electronegative atoms that take place through the covalent bonds. Okay, so here we have, this one is called butanoic acid on the left. Its pKa is 4.82. Okay, let's jump over to the other side. We have 2-chlorobutanoic acid. Okay, so when the proton is removed, we get a negative charge here, and we have this nearby chlorine, which is pulling electrons through the covalent bonds, and that helps to spread out and stabilize the negative charge. Okay, notice what happens as we move the chlorine farther away. Okay, the effect drops off very quickly. Okay, so here Comparing 2-chlorobutanoic with butanoic, that's a difference of 2 pKa units. Each pKa unit, remember, is a power of 10, so this is 100 times more acidic than butanoic. By the time we get to the fourth carbon over here, the effect is nearly gone. Okay, so this is called the inductive effect, where some electronegative element is pulling electrons through the sigma bonds, through the covalent bonds. Okay, here's some more examples of inductive effects. Okay, we have acetic acid as our basis of comparison. It's 4.76. If we replace one of these hydrogens with a fluorine, okay, now the pKa is 2.7, so that's a 100-fold increase in acidity. We see a noticeable effect with chlorine, but not as much as with fluorine. And we still see an effect with bromine and iodine, but they're less electronegative, so the effect is not as great. Okay, let's compare acetic acid again as our basis. If we replace one hydrogen with a chlorine, it's 2.8. If we replace two hydrogens with each with a chlorine, now the pK is 1.3. And trichloroacetic acid, where we've replaced this, this H shouldn't be there. Should just be CCl3. Now the pKa is 0.6. Okay, so that's a 10,000-fold increase in acidity. Hybridization. Okay, there are three main hybrid atomic orbitals that we talked about in the previous chapter. There's sp, sp2, and sp3. Sp would have a linear geometry that's usually associated with triple bonds. sp2 would have a trigonal planar arrangement, usually associated with double bonds, and then sp3 would be tetrahedral. Okay. So here we have, this is ethylamine, and its pKa is 10.6. And then here we have this imine salt, IMINE, an imine salt. And you can see that it's a stronger acid. It has a smaller pKa. Okay, in this case, the lone pair is in a sp2 orbital. Okay, so this is a trigonal planar arrangement. We have 3 electron-rich groups, so they're approximately 120 degrees apart. Here we have 4 electron-rich groups, approximately 109 degrees apart. Okay, we see this with CH bonds as well. Okay, I'm going to start down here at the bottom. Okay, this is acetylene. It has a linear geometry. It's sp hybridized. Its pKa is 25. This sp2 hybridized CH bond has a pKa of 44, and then the sp3 or tetrahedral has a pKa of 50. Okay, so this is tied in with the percent S character. Okay, so if we combine an S and a P, that's 50% S character. Okay, the explanation given is that if there's more S character, the negative charge can be held closer to the nucleus, and that results in greater stability. Okay, resonance is a big factor in acidity. Here we're comparing ethanol and acetic acid. The difference in pKa values is about 11, so that's 10 to the 11th power, 100 billion. Acetic acid is much more acidic. And that's because once this proton is lost, the negative charge can be delocalized over both of these oxygen atoms. In the case of ethanol, we lose a proton. That negative charge is just fixed on that oxygen. We can't spread it out. It's there on that oxygen, and that's where it stays. If we think about some of the strong acids, okay, other than HCl, HBr, and HI, if we have something like nitric acid, all right, nitric acid forms the nitrate ion. Okay, this is the nitrate ion. This can be resonance stabilized. Okay, nitrate ion is NO3 minus. The individual formal charges need to add up to the overall charge, which is -1. Okay, and then there's one more resonance structure. And that would involve the double bond being here. All right, so the negative charge is spread out by resonance. Okay, so this is very stable. So nitric acid is one of the strong acids. Similarly, with perchloric acid and sulfuric acid, we also have resonance stabilization. Okay, the example that's listed here down at the bottom is methane sulfonic acid. Draw the structure of that. Okay, so again, this negative charge can be delocalized over all three of these oxygens. Okay, this is a third row or below element, so it can exceed the octet rule. Okay, it's using d orbitals for bonding. Okay, so this is a fairly strong acid as well because the conjugate base is resonance stabilized. Right, this is actually going to be a major concept all throughout the course, and that's Lewis acids and bases. Lewis bases, also called nucleophiles, are species with available electrons that can be donated to form a new bond. Lewis acids are species that can accept these electrons to form new bonds. Okay, since the Lewis acid accepts a pair of electrons, it's called an electrophile. Okay, so a nucleophile donates electrons to a nucleus with an empty orbital. An electrophile accepts a pair of electrons. And when forming a bond, the nucleophile attacks the electrophile. So when we draw arrows, the arrow goes from negative to positive. And remember that, we always go negative to positive. Okay, when breaking a bond, the more electronegative atom receives the electrons. Okay, so here are several examples of Lewis acid-base reactions. Okay, the first example is just a general reaction where B represents the Lewis base. The proton can be a Lewis acid, but this definition is actually much broader than Bronsted-Lowry. It includes Bronsted-Lowry acids and bases, but also includes many more species. Okay, so the donor, we draw the arrow from the base to the acid. Okay, this next one doesn't even involve proton transfer. Excuse me. So ammonia donates a pair of electrons to boron. Boron has an empty p orbital that can accept those electrons. And we get an addition product. We have a bond formed between nitrogen and boron. Okay, here we have CH3O minus. That's the nucleophile. There's a lone pair of electrons on the oxygen. Okay, when it forms a bond to carbon, that gives carbon too many bonds, and so chlorine leaves, taking this pair of electrons with it, so it becomes a chloride ion. And we have a bond formed between oxygen and carbon. Okay, chloride has to leave or carbon would exceed the octet rule. Okay, and then this one is both a Bronsted and a Lewis acid-base reaction. Acetic acid is the electrophile. Ammonia is the nucleophile, so it donates a pair of electrons to the hydrogen. And again, hydrogen would have too many bonds, so it gives up this pair of electrons to the oxygen. Okay, so this bonding pair ends up as a non-bonding pair here. Okay, we're going to change to a different topic now. And this is the idea of functional groups. Okay, one of the things that we'll notice throughout organic chemistry is we'll see certain patterns of, certain structural patterns of atoms that occur with great regularity. And we classify those into functional groups. These subunits often behave in a predictable manner. Okay, so functional groups allows us not only to predict, in many cases, what reaction will occur, but it also forms a basis for systematic naming. I mentioned in the first day of class that there are about 10 million different organic compounds that are known, and it would be impossible just to go through and assign those an individual name, and so there's a systematic method. In fact, there are actually computer programs. You can draw a structure, and the program will use the systematic rules, and it'll give you a name. Okay, we're going to start with hydrocarbons. The hydrocarbons are not a functional group, but they're a general class. And the hydrocarbons include these functional groups. Alkanes and cycloalkanes are often considered part of the same group. Hydrocarbons contain only carbon and hydrogen. When I use the term heteroatom, I'll talk about heteroatoms. Heteroatom is some element other than carbon and hydrogen. Okay, so oxygen, sulfur, chlorine, nitrogen, okay, those are what we call heteroatoms. Okay, alkanes are hydrocarbons with only single bonds. All the carbons are sp3 or tetrahedral. Cycloalkanes typically react similarly to alkanes. They also have sp3 tetrahedral carbons, but they'll form rings. Alkenes are hydrocarbons that have one or more carbon-to-carbon double bonds. And those double bonds will consist of two sp2 or trigonal planar carbons. Okay, you also have cycloalkenes, where we have a double bond as part of the ring. And then there are alkynes. And alkynes are hydrocarbons that have a triple bond present. The carbons in the triple bond are sp hybridized, and they form a linear geometry. Okay, second semester, we actually have a whole chapter on what we call aromatic compounds. For our purposes, right now, we're going to say aromatics are like benzene. Okay, so these are the names of the first 10 straight chain alkanes. Okay, you do need to know these from memory. We have methane, they're classified according to the number of carbons. Methane, here's ethane, propane, butane. This one here is on a place. Pentane would be a string of 5 carbons, okay, and then up to 10. Hexane, heptane, octane, nonane, decane. This is an example of a branched alkane. Okay, and then here we have some cyclic alkanes. Okay, here we have cyclopentane. Okay, this is the full Lewis structure. It's often just written as a regular polygon. Cyclohexane, written as a regular hexagon. Okay, these actually react very similarly to open chain alkanes. All right, so here are some examples of alkenes which have a double bond. Okay, we have 2 different names here. Ethene is the systematic name. Ethylene is the common name. And we'll talk about that in more detail. Propene or propylene. You notice the similarity here to ethane and propane. Okay, alkenes will end in ene. But we'll talk about how to systematically name alkenes when we come to that chapter. But we can recognize alkenes, they'll have an ene suffix. Okay. These are positional isomers. Okay, the double bonds in a different place. But1-ene and but2-ene. Okay, and then here we have this heading is wrong, it should say alkynes. This is ethyne, commonly called acetylene. Okay, propyne, and again, notice the yne suffix or ine suffix. Okay, we'll learn how to name those systematically in a later chapter. Okay, so here is benzene. Okay, here's the full Lewis structure of benzene. And here's the line angle formula. Okay, these compounds contain that benzene ring. This is the general formula for a substituted benzene. Okay, so here's that symbol R. R is some indefinite carbon group. Okay, so this could be a CH3, it could be 2 carbons, it could be 100 carbons. Okay, and generally, as long as the carbon chain is all single bonds, it's really not going to do much in a reaction. It's the benzene that's going to react. Okay. Often the question comes up, if we look at the structure of benzene, we write this as a hexagon with alternating double bonds. We go back here, these are the alkenes. Okay, so why isn't benzene an alkene? Okay, well the answer is it reacts very differently from alkenes. And so it's put in a different class. Benzene is not the only aromatic compound, but for our purposes right now, we're going to say aromatic compounds, also called arenes, are derivatives of benzene, or similar to benzene. Okay, next we'll begin to look at some organic compounds that contain oxygen. Okay, so here we have alcohols. Alcohols have the general formula ROH. Again, R is some indefinite carbon group. Okay, these are all alcohols. It has an OH group. An ether differs from an alcohol. Instead of being carbon, oxygen, hydrogen, it's carbon, oxygen, carbon. Okay, so these are examples of ethers. Diethyl ether, furan, methyl terpenyl ether. Okay, a CO double bond occurs very commonly in organic compounds. The CO double bond is not really a functional group, but it's a part of several functional groups. CO double bond is called a carbonyl group. And 2 functional groups that contain the carbonyl are aldehydes and ketones. Okay, the difference is that an aldehyde will have a hydrogen on one or both sides of the carbonyl carbon. A ketone will have 2 bonds to carbon. So this is acetone. Okay, we use that in the lab a lot to wash glassware. And this is a cyclic ketone here, cyclohexanone. Okay, this is an aldehyde, C double bond O, and then H. Okay, and then a carboxylic acid. So this will be the last one that we'll look at today. Carboxylic acid will have a C double bond O, OH. Okay, notice the difference here between the carboxylic acid and the aldehyde. Okay, the aldehyde doesn't have that extra oxygen. Okay, so these are carboxylic acids. Okay, so I'm going to go ahead and stop here. And I'm going to end the meeting. And I will see you in lab tomorrow.